Hello, everyone. My name is Jason Mohoney. I am a graduating PhD student at UW-Madison and incoming postdoc at MIT. And I'll be talking to you about our work, which is Quake, adaptive indexing for vector search. This was work done at UW-Madison, but in collaboration with collaborators at Apple. So with the explosion in generative AI and embedding-based machine learning models, vector search has become ubiquitous. It is present in retrieval-augmented generation pipelines, multimodal search and general purpose search pipelines, as well as recommendation models. In its simplest form, it is about getting the top k nearest vectors to a query vector by a given similarity metric, such as L2 distance or inner product. But as the size of your embeddings or vectors grows, brute force in this becomes computationally infeasible. And so what people do is they use approximate indexes to allow for scalable vector search. And the simplest form of index is the partitioned vector search index, where an example of this is a FICE IVF index. And here you cluster the vectors in your set, and you cluster them into partitions using a clustering algorithm such as k-means, so that each partition is represented by a centroid. Then, when queries come in, they first scan centroids to find their most similar partitions, and then scan those partitions. So in this example, we scan a single partition, and the number of partitions you scan is a parameter known as nprobe. This is the parameter that controls the recall versus query latency trade-off. Updates to these indexes are relatively simple. In the case of inserts, you scan centroids for your inserted vectors to find the most representative partition, and then you append to the end of them. But the issue with updates is that they cause imbalance in your index, and this negatively impacts the performance of your index. And so this imbalance is exacerbated by the fact that workloads exhibit skew both in reads and in writes. So in this figure here on the left, we see the skew present in a workload we derived from Wikipedia. The top shows the access frequencies by search queries of partitions, where there are 1,000 partitions in this index. And the bottom shows the write skew, the amount of inserts to the partitions in this index. So we can see that certain queries are searched more often than others, meaning that these partitions dominate search performance. And then in terms of inserts, you see the skew is quite severe. Some partitions getting hundreds of thousands or millions of inserts, causing extreme imbalance. And so the way to resolve this imbalance is by maintenance, by splitting and merging partitions, where splitting is done using k-means. So this allows you to keep your index balanced, but the issue is that when you are supplying future queries after doing maintenance, your number of partitions has changed. So you have to tune to figure out how many partitions you need to scan in order to meet a given recall target. So in this example, now we have to scan 2 partitions, as before we had to scan 1. So to quantify this a little bit, let's look at the performance in terms of latency and recall of 2 types of partitioned indexes, FICE IVF, which does not do any maintenance, and scan, which does splitting and merging. On the top, you'll see the latency to process this Wikipedia workload over the lifetime of the workload, and at the bottom, you'll see the recall. So you can see that FICE IVF, its performance explodes over time because the partitions become imbalanced, and it has to scan extremely large partitions in order to reach a recall target, a high recall target. Scan is able to mitigate this through splitting and merging, but if you look at the recall plot, you see that its recall falls off a cliff. And this is because it's constantly adding more partitions to the index, and therefore you need to tune nprobe as this happens, tune the number of partitions you're scanning as this happens. So that brings us to our approach, Quake, which is an adaptive approach. It has 2 main contributions. The first addresses index imbalance and workload skew through cost-driven maintenance. And so here we have a maintenance methodology that monitors the access patterns of the index, identifies the partitions that are most negatively contributing to index performance, and then we'll go and target maintenance towards those partitions through splitting or merging. Then the second piece, because we are doing maintenance, we want to avoid this recall degradation. We designed a method called adaptive partition scanning. This allows the user to set a recall target, and then the system will figure out exactly how many partitions to scan to meet that recall target without any additional tuning. And so the result of this was an index that gives you 1.25x to 28x lower query latency then state-of-the-art graph index discan-n, and state-of-the-art partitioned index scan without tuning of n-probe, and we made this system open source. So for the remainder of the talk, I'll go into details of these two contributions and then do a little bit of evaluation at the end. So the idea behind maintenance, beginning with maintenance, is we use a cost model which models the query latency. And we use this to determine which partitions we need to split and merge. So there is a total cost for the index, where the total cost is simply the sums of the per partition cost terms. So each partition contributes to the cost based on the access frequency of that partition, times the size, or sorry, times the latency to scan that partition. And then there's a little bit of overhead for each partition due to the centroid. You have to scan that centroid for every query. And so the idea here is that we estimate the change in cost from splitting or merging, and then if that action is estimated to reduce the cost, then we take it. And so this allows us to minimize the cost model through maintenance. So let's build a little bit of intuition here by looking through a concrete example. So before we saw this picture about how you split with k-means, and so let's look at how this impacts the cost. So before splitting here, as I said, splitting is determined by access frequency, the time it takes to scan the partition, as well as the overhead. So in this example, let's say this partition is scanned by 10% of the queries. It takes 20 microseconds to scan the partition, and then the overhead to scan a centroid is 100 nanoseconds. So if you plug in the cost, this results in a cost term of 2.1 microseconds. Now let's look at an example split. Let's say we've done the split into two, and now we see that the left partition here is scanned by 5% of the queries. It's gotten smaller, of course, and the right partition is scanned by 8% of the queries and has also gotten smaller, so the time to scan these partitions is reduced. And splitting here, it's important to note that it reduces the cost because not all queries are going to scan both partitions. Some will go left, some will go right, some will be both, but overall it will reduce the cost. So if you plug this into the cost equation, we see that in this toy example, the cost after splitting is about 1.56 microseconds. So that's reduced over the initial partition. But the catch here is that we don't know these access patterns until after we've split and after we've collected statistics. So we need to estimate them. And so what we do is we introduce a parameter here called alpha. And this is just the expected decrease in access frequency for the partitions. And we assume that it's going to be roughly equal between the left partition and the right partition, so that they are decreased by an amount proportional to the access frequency of the original partition. And so if we just put some concrete numbers in here, let's say we put alpha equals 0.8. So we assume that 80% of the queries go left, 80% of the queries go right of that original 10%. Then the estimate for this split is 1.8 microseconds. That's less than the original one. And so based on our estimate, we should conduct the split. Of course, in practice, there's variability. You know, maybe this is an overestimate or an underestimate, but we are tuning here for the average case with this alpha parameter. So now let's talk about adaptive partition scanning. And this is our method for determining the number of partitions we need to scan in order to meet a recall target. And this method, I want to be clear, is online, and we do this per query. So we developed a geometric model, which takes into account the geometry of the query and the neighboring partitions around it. So around each query, as you see on the right side of the figure, you see there is this sphere around the query where the radius of the sphere is the distance to the kth nearest neighbor. And so as we're scanning partitions, we have a current estimate of what the distance to the kth nearest neighbor is, and so that defines this hypersphere around the query, which is like our search radius. And the idea here is we want to estimate what the recall is by scanning a partition, okay? And the key insight here is that the amount of overlap of this query hypersphere with the cluster boundaries or with the clusters is proportional to the amount of recall that you get from it. So from this, we produce a recall estimate based on this volume of overlap, and then we keep scanning partitions until our estimate has exceeded some recall target. And so there's more details about that in the paper, as well as the cost-driven maintenance. But now let's turn our attention towards valuation. So first, I'm going to show a comparison and a comparison of state-of-the-art indexes on the Wikipedia workload that we derived. And then we'll do a comparison of adaptive partition scanning with existing tuning-based methods. But there's a lot more in the paper where we look at things like NUMA-aware query processing and parallelism, multi-level indexing, batch processing, there's ablation studies, as well as additional workloads and baselines. So to begin, let's discuss our comparison on this Wikipedia workload, where this Wikipedia workload we derived from the growth of Wikipedia pages over time, where there's embeddings for each of these Wikipedia pages. And in this case, the index is growing from 1 million vectors to 12 million vectors over the course of the workload. The vectors are 128 dimensions, and we're interested in each query trying to find the top 100 nearest neighbors for a recall target of 90%. And here the queries are sampled according to Wikipedia page access counts. So this allows us to benchmark our algorithm in the context of skew. And the queries here are executed one by one. So we compared Quake in two configurations, a parallel configuration where we use intra-query parallelism, and we have a single-threaded comparison for fairness with the baselines, since the baselines do not support intra-query parallelism. We're comparing against FICE IVF, which does no maintenance, as we discussed before, Scan, which does splitting and merging, and we're comparing against DiskANN, which is state-of-the-art graph index, and we're looking at search, update, and maintenance time, the total times in hours for this workload. So our first takeaway is that in comparison to partitioned indexes, specifically Scan, we are 28x faster in our parallel configuration and 5x faster in our single-threaded configuration in terms of search latency. And this is because of two reasons. This is because of our cost-driven maintenance, which allows us to target the partitions that are most negatively contributing to performance, and our adaptive partition scanning, which allows us not to overshoot or undershoot the recall target over the lifetime of the workload. And the second takeaway is that in comparison to graph indexes, DiskANN, we achieve a 8x lower query latency in our parallel configuration and 1.25x in our single-threaded configuration. And what this represents here is a significant advancement over existing partitioned indexes. Traditionally, graph indexes have been superior in terms of search latency, and so this allows us to become much more competitive for this. So in this case, we were able to exceed their performance in both the single-threaded and parallel configuration. Now, I'd like to turn our attention to the comparison of adaptive partition scanning with tuning-based methods for meeting recall targets. And so what you're looking at here is APS versus two baselines. One is LATE, which is a machine learning-based method for setting N probe, which was published in SIGMOD 2020, and Oracle, which allows you to find the optimal N probe for query. And we're going to be comparing these two baselines against APS with 3 different recall targets, 80%, 90%, 99%, and we're looking at the recall, latency, and tuning time. So first thing, looking at recall, we see that APS is able to meet the recall targets, just like the baselines are. The second thing is that APS does not introduce a lot of overhead from its computation of its geometric model, only a 10 to 30% increase in latency over the Oracle. And then finally, this is the main thing, is that we don't need to do any offline tuning. This is all lightweight online, so that as your index is changing, you don't need to go and do costly offline tuning so that you can meet your recall targets. So with that, that's been Quake, an adaptive indexing system for vector search. It has two main contributions, cost-driven maintenance, which allows us to address index imbalance and workload skew, and then adaptive partition scanning, which allows us to address the recall degradation issue when you are conducting maintenance. And so we're able to get good performance, 1.25x to 28x lower query latency than state-of-the-art indexes, both graph and partitioned indexes, and we don't have to do any tuning for nprobe. So system is open source, email's there, but now I'm happy to take any questions.